Utah. I have flown myself halfway across, a little ways across, 2 hours worth of riding in an airplane and a little bit of shuttle riding to see my parents here in kind of near St. George. Kind of a weird timing for me, but I wanted to try to get your acids and base lecture kind of going here. So we are in the last week of a quarter, which has gone very fast. We had 8 weeks worth of work here, and we had 11 different lectures, so that's a lot of work. So if you're feeling tired, I feel your pain. So we're going to go ahead and jump right in to talk about acids and bases, and I think I'm going to try to do this in maybe about 3 little lectures. What we want to do is we want to talk about acids and bases, and you're pretty familiar with those from maybe those videos you watched on the demos. So we're going to talk specifically about how we identify an acid and a base. We are going to look at acid-base reactions. So we're going to look at how those reactions occur. And then we take a little pause and we talk about equilibrium and Le Chatelier's principle. Okay. And then we talk about the pH of a solution, calculate that, and then basically all that leads up to the conversation about buffers, which are the things that we have in our bodies that keep us at homeostasis. So we want the pH of the blood to stay at about 7.4, and so basically we have lots of buffers in our blood that help us do that, and you'll talk a lot more about that in your biology class. Okay, so essentially we want to talk about the types of acids and bases, and I guess what I will say to you is if you remember what you learned about strong and weak and non-electrolytes, then you have a big head start. And essentially a strong acid is a strong electrolyte. And so if you understand what an electrolyte is, meaning it's something that produces ions, right? It goes in one direction, then you understand what a strong acid or a base is. And we don't spend a lot of time talking about bases. So that's kind of one point. If you understand the weak electrolyte, then you understand about a weak acid. And basically, that is going to be a weak electrolyte, meaning it produces some ions, but not all ions, and that we have this system where it's at equilibrium. So we have ions, and then we have some so non-charged particles, I suppose we could say. And this equilibrium, hopefully you've watched a little video on equilibrium, and we'll talk a little bit more about that. But basically, these ions are in equilibrium with the original substance or the reactants, and there's not as many ions produced. So it turns out that weak acids are much more important to us. They are the ones that are in our biological systems that help us maintain these homeostasis situations. And so we need to talk about kind of what makes up buffer, and we'll kind of use some vocabulary to do that. Okay, so when we talk about acids, we have a couple definitions, but basically, if you think about it, we can call it an acid is a proton donor. Our classic acid is hydrochloric acid, and when hydrochloric acid reacts in water, it produces hydronium, H3O+. Sometimes we just call it H+. So this ion right here, H3O+, is called hydronium. And that was one of our polyatomic ions we spoke about a long time ago when we looked at our polyatomic ions on the sheet right here. There's that hydronium ion that we spoke about. The other ion that's super important to us is hydroxide. So we'll get to that. So if there's a substance that produces a base, that is a base, it's going to produce OH in solution. This is the hydroxide ion. And for some reason, these are the things that make acids and bases. So a Bronsted-Lowry definition, an acid is a proton donor. I should put that right there, like HCl. Let's see, CH3COOH are our favorites. And the bases, NH3 is a base. Our classic base is NaOH. Okay, and these, again, just to kind of put these two things back together, proton donor is an acid, and a proton acceptor is a base. Now, this actually goes back, for me anyway, to the conversation about oxidation and reduction, right? Oxidation is loss of electrons, and reduction is gain of electrons, right? And we're, it's which this electron is being passed over to this substance, and that's kind of what we're doing here. When we talk about acids, it's like the hydrogen ion. We're seeing who's giving it and who's getting it, basically. So it's kind of very similar in my head anyway. And I've given you some examples. So we talked about hydrochloric acid, acetic acid. We've talked about ammonia and sodium hydroxide. Okay, so let's keep going. So basically, Bronsted-Lowry definition of an acid has to have a hydrogen to donate in order to be an acid. So those species right there would be sort of our good candidates for a Bronsted-Lowry acid. If something doesn't have a hydrogen to donate, it can't be an acid, okay? So one of the interesting aspects of this one right here, right, is there's a hydrogen, so this is COOOH, right? And we'll notice there's the carboxylic acid group, right? And so just thinking about, which of these hydrogens is going to be more loosely held, and that's the one that's going to get donated, okay? As far as bases go, Bronsted-Lowry bases, right, those have to be able to accept. So these guys are going to be the hydrogen donor. So they have to have a hydrogen donate. These guys are going to be hydrogen acceptor. So they have to have the ability to sort of take on a positive charge, right? So the ones that might make sense there are this OH, right? And it would end up as HOH or water, right? This substance right here is negative, so it's probably going to connect to that hydrogen and maybe become, accept that hydrogen. And you'll notice that the charge goes down. It was negative. We put that positive on there and it went to neutral. It was -3. We put that positive on there and it went to -2. And then this is the other species that might be able to accept a hydrogen. And again, it was negative. We added a positive and it went to neutral. So you'll notice that when the acids donate away, right, it's going to lose their hydrogen. So they're going to go, their charge is going to go down, and these guys, their charge is going to go up. So this one, when it donates a hydrogen, it's going to be HCOO minus, and then this one's going to be NO2 minus. So again, that's pretty swift, but acids are hydrogen donors, so they have to have a hydrogen to donate. Bases are hydrogen acceptors, so they have to be in a position where they're going to want to accept a positive charge, right? And all of these, this is neutral, this is neutral, this is neutral. This one, you might think about it as magnesium carbonate 2 minus. So if this is separate in solution, this has the possibility of accepting a hydrogen. And it would be just -1. Okay. So just again, being able to talk about what is an acid and what is a base. Okay, so let's talk about strength. Essentially, strong acids, as we spoke already, these are strong electrolytes. Okay, and they're classic hydrogen iodide, hydrogen bromide, hydrogen chloride, sulfuric acid, nitric acid. Strong bases, also strong electrolytes, classic sodium hydroxide, potassium hydroxide. Weak acids, we said, weak electrolytes in equilibrium. Okay, so we'll look at these reactions and I will go ahead and really speak about how that looks in terms of the equilibrium part, and we're going to get into that more. So in this reaction, this is the acid. So this must be the base. This is the hydrogen donor. And so when that hydrogen goes away, the leftover is the chlorine. And the leftover from accepting the hydrogen is the H3O plus. Okay, so I'm going to go ahead and throw these words out here because we need these later. This is going to be the conjugate. This is going to be the conjugate base, because and then this is going to be the conjugate acid, and we'll get to that better in a second, but I'm just going to write these down because I want to take those words and use them again and again. So this is acetic acid, reacts with water. It's the acid. It's going to donate the hydrogen to the water. The leftover H3COO minus and H3O plus. This is our acid, acetic acid. Base is water. The leftover is the conjugate base, and the leftover here is the conjugate acid. Now, a way to think about that more fully might be that this is a reversible reaction. This is in equilibrium, meaning, and I'll get to that in a second, that the forward reaction and the reverse reaction are equivalent. And if you think about in this reverse reaction, this is the acceptor of that hydrogen. So that makes sense that it's the conjugate base. This is the donor of that hydrogen, and that makes sense that it would be the conjugate acid. So that's another way to think about that. The NH3, this is the ammonia, so this is the base. And what's interesting is in this case, water is acting as an acid. It's going to donate its hydrogen. The leftover is NH4 plus and OH minus. Okay, so the big concept here is being able to notice who's the acid and who's the base. The other big concept here is identifying these conjugate acid-base pairs. Conjugate acid-base pairs. And this is just setting us up for understanding buffers. So once again, the acid does the donation, the leftover is the conjugate base, the base does the accepting, the leftover is the conjugate acid. And for me, a very easy, maybe a better way to think about it is in the reverse. When this substance accepts the hydrogen, that makes it a base. And when this substance provides the hydrogen, that makes it an acid in the reverse direction. Okay, so again, the reason we want to know this is we want to understand buffers later on. And perhaps you've seen the video already that Scott did. And he talked a little bit about how the system has to be at equilibrium in order for that buffer to neutralize any excess acid or neutralize any excess base. Okay, so there is a good place to kind of like pause and reflect. So I'm going to stop and just upload this short video for you.